Now we're going to use problem number 9.46 for this one-tail example. So the Los Angeles Transportation Authority has mechanical reliability goal of 3,900 bus miles. Bus mechanical reliability is measured specifically as the number of bus miles between mechanical road calls. Suppose a sample of 100 buses resulted in a sample mean of 3,975 bus miles. Okay, so the reliability goal is 3,900, and we want to test whether there is evidence that the population mean bus mile is greater than 3,900. Have we reached the reliability goal? Okay, we want to test whether that is so. So greater than 3,900, and we want to use an alpha of 0.05. So which means first we have to define the parameters. So x is the number of bus miles between mechanical road calls. So mu is the average, sigma is the standard deviation. So given that, we have a sample summary of 100 observations. We took 100 random samples, and then it turned out that the number of bus miles is 3,975 and a standard deviation is 275. Now what is the hypothesis? The hypothesis is about 3,900. Right? Put that 3,900 in a separate cell. The alternative hypothesis is what? We want to be able to tell that we have achieved the reliability goal. And to do that, we need to have strong evidence. So you have to put that in the alternative. Okay. See, remember, if you put that alternative, the greater than in the null, and then you are forced to put the equal to also. So if you put greater than or equal to, then you're not able to reject the null hypothesis. All that means is that you don't have sufficient evidence to reject the null hypothesis. So which means that you're going to stay mute. You're not going to say anything. That means you have not proved anything. So that's the reason why you shouldn't put the condition with null where you are going to stay mute. You're not going to say anything, and there is no point in putting it there. So what you need to put there is a case where you won't make any claim at all. So put that in the null. The alternative is mu greater than or equal greater than 3,900, and we want this to be tested at 5%. So we need the standard error, okay, which is square root of, which is s over square root of n. Okay, now this is a t statistic because sigma is unknown. So the t stat is x bar minus the mean mu divided by the standard error. That's our t statistic, and this is a one-tail statistic, and the alternative hypothesis is greater than, so it is the upper tail. So it's a positive number that we are after. Degrees of freedom is n minus 1. Okay. Now t table value, we can find the t table value from the table. So we want 5% at the upper tail and 99. So 5% upper tail, which is that, and we want 99 for degrees of freedom, and we have 99 degrees of freedom in the next page. 5%, if you go down all the way, you get 99% here, 1.6604. Okay, and that is t table is t sub alpha value. Okay, and I'm going to use the, okay, so we looked at the t table here, but we can also get the t value from Excel. Again, you don't want TINV. TINV is legacy. So you want T dot INV. Now we don't want T dot INV dot 2T because that would give us a two-tail value. So we want T dot INV, okay, and we need to give the probability and degrees of freedom. Okay, we want to give the probability is the cumulative probability, okay, in T dot INV. So cumulative probability means this is the upper tail, so you have to go 1 minus alpha, and then the degrees of freedom is 99. Then that gives us the same alpha, same T table value like what we got here. So conclusion is your T stat is greater than the T critical value, so we reject null hypothesis. Now p-value, okay, it's going to be difficult to find the p-value from the T table, so we will use the Excel function. So here we have T dot dist. Okay, so here we have three functions: T dot dist, the cumulative function, T dot dist 2t. When you have a two-tail test, what would be the probability? And RT would be simply the one-tail test on the right side. So what we have is a one-tail test on the right side. So this is the right side tail, and we give the T value and the degrees of freedom, T dot dist dot RT. So you have to think about which T dot dist function you have to use. T dot dist will give you the cumulative probability, which is good for left side T tail. T dot dist dot 2t will give you a two-tail test p-value. Whereas T dot dist dot RT will give you a p-value for one-tail test on the right side. So that's your p-value. Let's make that into a percentage, if you will. So since p-value is less than alpha, we reject the null hypothesis. So now we have to interpret. Once again, remember, there are two parts of the interpretation: that we have sufficient evidence or we do not have sufficient evidence to reject the condition stated in the null hypothesis, and then the probability of type 1 error. So here, we have sufficient evidence to conclude that the average number of bus miles between mechanical failures is greater than 3900, the condition stated in the alternative hypothesis. We have evidence to go with that alternative. We can now take a stand. And the probability that is a mistake, that we're making an error, is only 0.38%. It's very small, so we can afford to take that risk.